The second is to design DC ammeter and DC voltmeter using the ensemble instrument. Okay, the third is to design multi-range DC ammeter and DC voltmeter using air tension. And then define low error and ammeter insertion effect. And the last one is to design ohmmeter using the ensemble instrument. We will learn about PMMC, permanent magnet moving coil, DC ammeter, DC voltmeter, DC meter effect, and ohmmeter. Okay, this is an introduction. Basic meter movement in galvanometer used in DC measurements can be traced to Hans' discovery in 1820 in the relationship between current and magnetism. It was the first instruments used to detect and measure small amounts of electric current. So, galvanometer is the first instrument to detect small amounts of electric currents. And then, he patented the moving coil galvanometer. The same basic construction developed by the ensemble is used in meter movement today. PMMC, instrument meter movement, referred to as the ensemble meter movement. So PMMC can be referred as the ensemble meter movement. So the name ensemble is because of the owner or the founder of the moving coil. This is an early ensemble galvanometer showing magnet and rotating coil. This is galvanometer. Have you seen galvanometer before? Have you seen in lab or maybe at your home? Have you seen this meter before?
Yes.
Yes.
Not the left one though.
Lab one. Okay. So this is galvanometer. As I mentioned to you last week or last 2 weeks, galvanometer detect or indicate electric current, small electric current. So the middle scale is 0. So if the circuit is balanced, so the needle indicate to 0, meaning that 0 current. Okay. If the circuit is unbalanced, so the needle will deflect to the right or to the left. PMMC used 2 permanent magnets in order to create stationary magnetic field. The application of PMMC is ammeter, voltmeter, galvanometer, and ohmmeter. All the meter types. Okay, this is construction of PMMC. This is cylindrical shaped soft iron core, the black one. It is placed between north and south, which coil iron or fine wire is wound. So coil is wound around the soft iron core. This fine wire is wound on very light metal frame and mounted in a dual setting so that it can rotate freely. We have pointer or needle. Deflects upscale as the moving coil rotates. Okay, when the moving coil rotates, so this pointer or needle will deflect up scale. Okay, this is the diagram of the ensemble meter as the current flows from positive, from here, positive, through the coil, okay, the orange one, to negative. So from positive, the current flows through negative. A magnetic field is generated. A magnetic field is generated in the coil. This field is counteracted or responded by the permanent magnet and forces the coil to twist, moving the pointer in relation to the field strength caused by the flow of current. Okay, the same figure. Okay, when a current flows through the coil, it generates a magnetic field which is proportional to the current in case of an ammeter. The poles of the electromagnet interact with permanent magnet, causing the coil to rotate and the pointer deflects upscale. it should be emphasized that the observer meter movement is a current scale calibrated. The moving coil responds to the amount of current through its windings. Okay, working principle is based on Moto principle where when a current carrying conductor is placed in the magnetic field, it is acted upon by a force which tends to move it to one side and out of the field. The deflection of the pointer is directly proportional to the amount of current passing through the coil. Okay. Amount of rotation is proportional to the amount of current flows through the coil. The meter, okay, PMMC or the observer meter requires low current, about 50 microamps for a full scale deflection, meaning that for the needle to deflect at full scale, so it will require low current, about 50 microamps. This consumes very low power, about 25 to 200 microwatts. The accuracy is about 2% to 5% of full scale deflection. You can watch this video later about PMMC movement. So I have uploaded a PowerPoint slide in Microsoft Teams. So you can just click the when you enable slideshow, you can just click the link to watch the video. This is DC emitter. So the PMMC galvanometer creates the basic movement of an DC emitter. So if you can see this part, okay, so PMMC or the observer configuration is here. Okay, so that this configuration will create emitter, voltmeter, ohmmeter. Okay, so emitter, voltmeter, and ohmmeter consists of PMMC construction. Okay, can you see coil here? And then, of course, you can see the needle. Can you see the coil here? Class?
Yes. Can.
Okay. So the coil winding of a basic movement is small and light. Okay, small and light. So it can carry only very small of currents. A low value resistor are shunt. Okay, this is the circuit diagram. Okay, the circuit diagram of meter plus PMMC. So this is PMMC or the observer construction. Here it is here. This one represent here. Okay, so this is meter movement. Okay, meter movement. Meter movement of the observer or PMMC here. Okay, the overall circuit. This is the overall meter construction of meter. Here the green one. The green is the meter DC emitter. Let's say this is DC emitter. So the green one is DC emitter. It consists of PMMC construction here. Okay, a low value resistor are shunt. This shunt resistor is added in DC emitter. Okay, so this is DC emitter, the green one. It has R shunt. Okay, shunt resistor to measure large current. Okay, because emitter has its range. Okay, so this shunt resistor measure large amount of current. R shunt is connected in parallel with meter internal resistance Rm. So Rm is internal resistance of PMMC. This is PMMC. PMMC consists of Rm and Im. Okay. So this is the total current that flow through the emitter. Okay. Here it divide into IM. Okay, IM is the current that flows through the PMMC or through the observer meter. Current flow here. Okay, so IM conduct very small of current. Okay, because the small size and the small size of coil winding of the observer meter. Okay, so the total current is equal to IM plus I shunt. Okay, usually IM is very small rather than I shunt. Okay, this is PMMC instrument. Okay, this is construction of DC ammeter. So the whole circuit is DC ammeter. It consists of PMMC instrument here. Okay, this is R shunt that is connected in parallel with the PMMC instrument. Okay, so imagine that total current will flow from here. It will divide into I shunt here and IM. Okay, so IM is small than I shunt, but R shunt is smaller than RM. Okay, because I is directly I is opposite to R, right? I is equal to V over R. So I is inversely proportional to R. So when IM is small, so RM is large. Okay, so we repeat the construction of DC ammeter. RM is internal resistance of the PMMC instrument, or for the coil resistance. R shunt is here. Okay, I shunt is the current flows through the R shunt. IM is the current flows through the PMMC. I, the large I, the big I is the full scale deflection of the ammeter. Okay, I is the current flows through the whole of ammeter, or the current to be measured, or the total current. Generally, I shunt is much greater than IM because PMC only needs small current to conduct the coil. Only small part of main current flows through the coil. Coil means the PMMC part. Only small current flows through the coil. Okay, so we come to the basic electric circuit. Basic that you have learned last semester. VM is IMRM. VM is the voltage drop across the PMMC construction here. Okay, so VM is equal to IMRM. V shunt is equal to the voltage drop across R shunt. So this is parallel connection. Of course, V shunt, okay, is equal to VM. I shunt is here, is equal to I minus IM, or IM is equal to I minus what? I shunt. Okay, can understand?
Yes.
Okay, so this is VM is equal to IMRM is the principle of what?
Ohm's law.
Ohm's law, good. Ohm's law only. Okay, so this is when we want to make R shunt as our target. R shunt is equal to V shunt over I shunt. Again, this is Ohm's law. R shunt is equal to V shunt over I shunt. And V shunt is equal to VM, right? VM is equal to IM RM. Okay, divided by I shunt is equal to IM RM is here. I shunt is equal to I minus IM. Okay, no need to remember this equation because this is the derivation from Arshan. Okay, so it depends on question. You just use Ohm's law and current, Kirchhoff current law. Okay, I is equal to IM plus Arshan is Kirchhoff current law. So only Kirchhoff current law and Ohm's law apply here. Okay, this is an example. Calculate the value of shunt resistance required to convert a 1 milliammeter movement with a 100 ohm internal resistance into a 0 to 10 milliammeter. Okay, imagine that this is design. Okay, you want to design a 0 to 10 milliammeter. Okay, so the question is to find Arshan. Okay, what is the value of Arshan required to build a ammeter with 10 milliamp range? Okay, the IM and RM is given. Okay, so 1 milliamp meter movement is IM, 100 ohm internal resistance is RM. Okay, because please be noticed on the sentence. Calculate the value of the shunt resistance required to convert a 1 milliammeter movement. When you see the term meter movement, meaning that it refers to the PMMC construction. So 1 milliamp is IM with a 100 ohm. 100 ohm is RM. Okay, so the question is to find R shunt. So R shunt is equal to V shunt over I shunt. V shunt is equal to VM. VM is equal to IM RM. I shunt. Okay, so it is equal to IM RM. I shunt. I shunt is equal to I minus IM. Okay, so now we substitute the value. IM is equal to 1 milli. Okay. RM is equal to 100 ohm divided with I. I is the total, the full scale deflection of the ammeter that to be designed, that we want to build. 10 milli. Okay, 10 milli minus IM is equal to 1 milli. Okay, so the answer is 11.11 ohm. This is the value of shunt resistance that is required. So if you are confused, what is IM, what is I? Okay, usually IM is much smaller than I shunt, and of course the total I, 10 milli. So here 1 milli is smaller than 10 milli. So 1 milli is IM, 10 milli is I. Okay, and R shunt is much smaller than RM. RM 100, R shunt 11. Any question?
No.
Okay. This is very basic. Okay. Previously we learned about single range. Okay, single range emitter. Now this is multi-range emitter. So in multi-range emitter we have different R shunt. This is R shunt. R shunt 1, R shunt 2, R shunt 3, and R shunt 4. This construction is to design 4 range emitter, because we have 4 shunt resistors here, meaning that we want to design emitter that has 4 ranges of current. Okay, the range of the DC emitter is extended by a number of shunts selected by a range switch, as is switch. The resistors are placed in parallel to give different current ranges. Switch S protects the meter movement from being damaged during range changing. Okay, this type of meter are used for range up to 50 amp. This is the precaution step when using this type of meter, start with selecting the highest current range, then decrease the range until good upscale reading is obtained. So you should start with the highest current range. Okay, if you cannot read the reading, okay, cannot read the measurements, then you decrease the scale. Okay, if you still cannot read the measurement, then decrease again. Okay, so decrease until a good measurement is obtained. The resistance used for the various ranges are of very high precision value, increase cost of the meter. Okay, so you can read this. What is multi-position switch? It made before break. Okay, meaning that the switch protects the meter movement from being damaged without a shunt during range changing. Okay, you can read this. This is about switch, multi-position switch versus ordinary switch. Okay, the meter movement never left unprotected. Okay, because of the usage of this switch. Okay, the purpose of designing the shunt circuit is to allow us to measure a current that is some number n times larger than Im. Okay, so again, no need to memorize this formula. Okay, it is better to you to apply basic principle of electric Ohm's law, KCL. What else? KVL. Okay, what else? Okay, usually in this chapter we only use KCL and Ohm's law. Okay, so you just use that principles. Okay, no need to memorize the formula. Okay, another example, design a multi-range ammeter to provide an ammeter with a current range of 1 milli, 10 milli, 50 milli, 100 milliamps. Okay, so we want to design an ammeter with 4 ranges. The observer meter movement with an internal resistance of 100 ohm and full-scale deflection current of PMMC instrument of 50 microamp is used. So the second sentence talking about PMMC construction. Okay, it has internal resistance Rm of 100 ohm and Im 50 microamp. Okay, so this value is very small, so this is Im. This is the range of the ammeter. So design. Okay, design. So meaning that we have to find the value of R shunt for each range. Okay, that's all. We need to find the R shunt. Okay, the current for each range is given. Okay, Rm is given, Im is given. So we have to find shunt resistance for each range. Okay, so R shunt is equal to V shunt over I shunt. V shunt is equal to Vm. Vm is equal to Im Rm. So Im is given, Rm is given, so Vm is 5 millivolt. For R shunt 1 is equal to V shunt or Vm divided with I shunt 1. Okay? So 5 milli divided with I shunt 1. I shunt 1 is now we want to design for this range 1 milli. Okay, so 1 milli minus 50 micro. Okay, 50 micro is Im equal to this. Okay, so for R shunt 2 is equal to 5 millivolt divided with I2. I2 is equal to 10 milli. Okay, same goes for other range. We substitute the total current for that range. Okay, here. So from this calculation, we can see that for R shunt 1, okay, the total current is 1 milli. The R shunt 1 is equal to 5.2. Okay, and then the total current becomes larger until R shunt 4. So at R shunt 4, the total current is 100 milli, but the R shunt 4 is 0.05. Why? Because current is inversely proportional to R. Any question?
No.
Can understand? Very well.
Can understand.
Okay. So I shunt. Okay. So I think the explanation is clear. The next type is R10 shunt. Okay. Compared to multi-range emitter that we have learned before, the R10 shunt or the universal shunt is frequently a more suitable design. It can eliminate the possibility of current overloading of the moving coil, where they protect the deflection instrument of an emitter from an excessive current flow. It may be used with a wide range of meter movements. R10 shunt eliminates the possibility of having the meter in the circuit without a shunt and reduce cost. Okay, this is R10 shunt where the resistor are connected in this arrangement. Okay, it is different with previous multi-range emitter. Okay, in multi-range emitter, the shunt resistance are connected in parallel. Okay, so this is at 1 is for range 1. Okay, 2 is for range 2 and 3 is for range 3. Let's say this emitter has 3 ranges, which is 10 milli, 50 milli and 100 milli. Okay, for an example. So for 10 milli the switch is at 1. Okay, for 50 milli the switch is at position 2 here, and the last one the switch is here. Okay, in at position 1, okay, at position 1 here, RA, okay, parallel with series combination of RB, RC and RM. Meter movement is RM. Okay, this is negative, this is positive. So now this switch is tapped at 1. Okay, at position 1, RB, RC and RM is series. Okay, this path is parallel with RA. Can you imagine? Can you imagine? Okay, we proceed. At switch, when the switch is located at position 2, okay, RA and RB in parallel. Okay, RA is connected in series with RB. This path is connected in parallel with RC plus RM. Okay, at position 3, RA, B and C in parallel with the meter. Okay, so when the switch is tapped at position 3 here, okay, here, so RA series with B and C, this path is parallel with RM. Can I understand?
Yes.
Yes. I need to redraw. Anyone? Boleh juga. Okay. Okay. Now Okay. Okay, so at okay, so when the switch is at position 1, okay, this is RA, this is negative, this is positive. Okay, so this is at position 1, right? Okay, and then we have RB, right? And then what else? R, C, and
Meter.
RM, right? Okay, so okay, now RA is parallel with what? RB plus?
RB plus RC RM.
Okay. Okay. So the voltage drop across RA is equal to the voltage drop across here. Okay. So how about this is at position at 1. Okay. So can you draw for position at 2? Can or cannot? Okay, now this is for position at 2, alright? At 2. How about at 2? Okay, we have, this is 2. Okay, so this is RB. I think you know this. So this is RA, right? RA. Okay, so this is negative. So like this, right? Can? Am I right? So RA plus RB is parallel with RC plus RM. Am I right?
Yes.
Okay, and then please proceed for position at 3. Okay, do it yourself. How about at switch 3? When the switch is set at 3. So what parallel with what?
RA plus RB plus RC parallel with RM.
Okay, excellent. Tepuk tangan. Okay. So let's go to other slide. Okay. So in general, the voltage drop across the two parallel branches is always equal, right? So V shunt is equal to Vm. Okay, V shunt is I shunt R shunt equal to Im Rm. Okay, but I shunt is always I, the big I minus Im. Okay, so now the equation is depends on the location of switch. At position 1, okay, R1 is parallel with R2 plus R3 plus Rm. So this is V, okay, V shunt is equal to Vm. So at 1, V shunt here is equal to I shunt 1, okay, multiply with R1. Okay, so the current flows here is I shunt. Okay, so name it as I shunt 2. So this is the large I. Okay, the total I is equal to I shunt 2 plus Im. Im is here. Okay, so here I is equal to I shunt 1 plus IM. Okay, and the same goes for I3. Okay, I3 is equal to I shunt 3 plus IM. Okay, so now the switch is at 1. Okay, so I shunt 1 is the current flow through here. Multiply with R1 is equal to IM in the bracket of R2 plus R3 plus RM. Okay, so mistake here. R2, okay, R2 plus R3 here. Okay, so please do the correction in your slide. Okay, I1 is the current range for position 1. I1 is here. Oh, I1 is here. Okay, I1 is here. Okay, it will divide into I shunt 1 and IM. Okay. Okay, this is where the switch is tapped at 2. Okay, so the voltage drop here is equal to the voltage drop at this path. Okay, so now R1 plus R2 is parallel with R3 plus Rm. And the voltage drop here is equal to the voltage drop here. The voltage drop here is I shunt 2 multiply with R1 plus R2. It is equal to the Vm. Vm is Im. Okay, Im is the same for all cases. In the bracket R3 plus Rm. Okay, this is where I2 is at position 2, meaning that for the second range. Okay. Okay, this is for position 3. So when the switch is tapped at position 3, R1 plus R2 plus R3 is parallel to Rm. So V here is same as the V here. V here is I shunt 3 in the bracket R1 plus R2 plus R3 is equal to Im Rm. Okay, and I shunt 3 is equal to I3 minus Im. Same goes for other position. I shunt 2 is equal to I2 minus Im. Okay. Okay. Here as well, I shunt 1 is equal to I1 minus Im. Any question? Yes or no?
No, Doctor.
Okay. So okay, now this method is not suggested to be used, okay, because I like to use only the principle of KCL and Ohm's law. Okay, this slide, okay, shows the derivation to find the value of RA, RB, RC. Okay, so usually during previous semester I explained this derivation, but I think no need to explain to you. If you are interested, you can go through by yourself. Okay, R shine is equal to this. Okay, and then substitute. Okay, substitute again, substitute to find. Okay, part B is when the switch is here. Okay, so yes, this is a mathematical expression. Okay, just substitute again until you get RC. Okay, but the value of current ranges can be found. Okay, but the value of current ranges can be found using Ohm's law and KCL only. The value of shunt resistor can be found using The derivation, okay. This is the derivation, okay. This example, okay, solve for shunt resistor by using formula. Formula is derived from the derivation that I showed you previously. So I'm not interested to that. Better use this solution. Okay, so this is an example. This is solution 1 that is recommended. The question is, where's the question? This is the question. Design an artificial shunt as shown in figure below to provide an ammeter with a current range of 1 milli, 10 milli, 50 milli, 100 milli. Okay. So this ammeter has 4 ranges of current. We can select 1, 10, 50, and 100 milli, depends on our measurement. The observable movement with an internal resistance of 100 ohm, this is Rm, and a full scale current of 50 micro, this is Im. Okay, so this construction, the observable movement has Im of 50 micro, Rm of 100 micro. Okay, so design, so meaning that find or R1, R2, R3, and R4. Okay. Okay, now Rm is given, Im is given. So you have to find each R shunt. Okay. So we know that V shunt is equal to Vm. Okay, for 1 milliamp range, meaning that when the switch is tapped here, okay, we know that all resistors are connected in series and this path is connected in parallel with Rm. Okay, and I shunt is always I minus Im, meaning that for I shunt 1, I shunt 1 is equal to I1 minus Im. Okay. So I shunt, R shunt, this is V shunt. V shunt is equal to Vm. Okay, so at 1 milliamp, okay, I shunt is equal to what? I shunt is equal to, how to get 950 microamp? How to get this? How to get this? How to get?
I tolak IM kan.
Okay, what minus what?
1 milliampere tolak
Hmm.
50 micro tu.
Okay, so at 1 milliamp range, so I shunt 1, this is I shunt 1. I shunt 1 is equal to I1 minus Im, meaning that 1 milli minus 50 micro. So 950 microamp. Okay, so in the bracket, R shunt is all the R1 plus R2, 3, and 4. Okay, equal to Im is given, Rm is given. So these are the summation of all R is equal to 5.26 ohm. Okay. Now we cannot find what is R1, R2, and R4. So better to start with here 100 milliamp. Better to start here. Okay. So let's start here. For 100 milliamp, this is I shunt 1. Okay. R shunt 1 is only R1, right? Okay, so please calculate now. So how to get 99950 micro? How to get? Calculate now. Get the answer. Class?
Dapat.
Right. Okay. Ikhwan, how did you get this value? How did you get this?
100 milliampere minus 50 microampere.
Again?
100 milliampere minus 50 microampere.
Excellent. Okay, so this is Aishan what? Aishan 1. Aishan 1, right?
Yes.
Aishan 1. Bolehlah Aishan 1, okay? Okay, multiply with only R1, okay, because the switch is tapped here, okay, at 100 milli. Okay, equal to IM 50 micro in the bracket of all the resistor at this path. Okay, R2, 3, 4 and RM. R2, 3, 4 and RM. Okay. Again, we cannot find because we don't know R2, 3, 4. Okay, so you can start at any switch. Okay, so now let's go for 50 milliamp here. So now I shunt 2 in the bracket R1 plus R2, okay, is equal to 50 milli multiply with R3 plus R4 plus RM. Okay, how to get this? 49950. Al-Amin. Al-Amin?
Yes, doctor.
How to get this value?
50 milliampere minus 2 IM, which is minus 50
Betul dapat ni. Did you get this?
Yes, dapat doctor.
Yeah. Okay. Who else? Muhammad Badrul. Badrul apa ni? Biasanya Badrul Amin. Okay. Badrul. Okay. For 10 milliamp. How did you get 9950?
I 10 tolak 20.
Again?
10 mili tolak 50 mikro.
Pandai. Okay. So now you have how many equation? 1, 2. Okay. And then you rearrange, substitute until you get this answer. Okay. You have 4 question. So by using your calculator, okay, some calculators can only solve for 3 equation, right? Okay, so so you can try this. I recommend you to okay, so you can try this by using usually in your midterm test and your final exam, the equation that to be solved is only up to 3 equation, okay, or 3 unknowns. Okay, usually not to 4 equation of 4 unknowns because we consider the limitation of some calculator. Okay. Okay, so this solution, okay, solution 2, it use derivation from the, okay, formula from the derivation, just substitute, okay. Okay, now we go to tutorial. Okay, tutorial. So tutorial 2, number 1 until number 3. Okay, number 1 until number 3 can be solved today. Okay, the rest for the next subtopic. Okay, so the question can be downloaded from Microsoft Teams. Okay, this is number 1. An ammeter as in figure 1. You want to take 5? Oh, no need. You may take 5. You want to go to toilet or what else?
Doctor, Saya ada satu soalan lah.
Hmm.
Potentiometer kita belajar sendiri
You can learn by yourself, but usually if I not cover that subtopic, meaning that what?
Tak penting.
Not. It is not important, but
Masuk exam.
huh?
Masuk exam ke?
Yeah, macam tu lah. It might not be asked in your final exam and written test, but you can read for your knowledge, okay?
Okay, Doctor, thank you.
Because subtopic potentiometer is very detailed, okay? Usually that subtopic have been covered during my lecture on during last semester, okay, last year, but I found that subtopic is very detailed and we skip this time, okay. Okay, you may take 5. Can we continue? Okay, an ammeter as in figure 1. Where is figure 1? Okay, this is figure 1. Figure 1 has a PMMC instrument. Okay, this is PMMC instrument. Where is ammeter? Okay, the whole circuit is ammeter. This part is PMMC instrument. Okay, with a core resistance of Rm 99 milli. Okay, so Rm is internal resistance. Okay, due to coil. Okay, 99 ohm and FSD current of 0.1 milli, meaning that IM is 0.1 milliamps. Okay. Shunt resistance Rs, okay, R shunt here is equal to 1 ohm. Okay, so Rm is much larger than R shunt. Determine the total current passing through the ammeter, meaning that I here. At full scale deflection, B 0.5 full scale deflection, C 0.25 FSD. Okay, so at A, FSD is meaning that at 100% of full scale deflection, meaning that, okay, determine the total current when this needle can deflect at 100%. Okay, so this is 0 at 0 M. Okay, no deflection. For full scale deflection, meaning that for full scale of range, okay, how much the current? Okay, the range of the current. B 0.5 full scale deflection. So determine the total current at 0.5 full scale deflection, meaning that if the needle is located at the middle, okay, 0.5 at the middle. At the middle, what is the current? Okay, C 0.25 full scale deflection, meaning that this is the full scale. Okay, we want 0.25 only. Okay, 0.25 is about here, right? Okay, here. Okay, here. So what is the current? What is the reading? What is the reading of the ammeter? Okay, so A at FSD, we need to add 100% of full scale deflection. I is equal to IM plus I shunt. FSD is IM plus I shunt. So what is IM? IM is given. What is I shunt? I shunt is not given. I shunt is equal to V shunt. Okay, I shunt is here. I shunt is equal to V shunt divided with R shunt. And V shunt is equal to VM. VM is equal to IM RM. Okay. So IM, substitute IM, substitute RM. Okay, and R shunt. R shunt is 1. Okay, so I shunt is equal to 9.9 milli. Okay, I shunt 9.9. This is okay, 9.9. Okay, so now we want to find I. I is equal to IM plus I shunt. IM is 0.1 milli. I shunt is equal to 9.9 milliamps. So the total I is equal to 10 milli. Okay. So how about 0.5? Just multiply with 10 milli. This is the full scale. How about 0.25 full scale deflection? Just multiply with the full scale 10 milli and you will get this answer. This is 0.5 full scale deflection. This is 0.25 FSD. Any question? The basic question? This is basic. Any question? Can I understand? Can understand? Okay. Okay, this is number 2. A PMMC instrument has a FSD of 100 microamp, meaning that it is I what? I
IM.
am, okay, because this value follows the term of PMMC instrument, okay, so meaning that this is for PMMC or the ensemble, and a core resistance of 1K, so 1K is R what?
M.
Huh?
RM.
RM, okay, good. Calculate the required shunt resistance, so R shunt, to convert the instrument into an ammeter with FSD 100 milliamp. The second is FSD 1M, meaning that for A, we want to design an ammeter with scale 100 milliamp, okay, with the range of 100 milliamp. What is the R shunt? Okay. The second one is we want to design an ammeter with 1 amp range. Okay. So what is the R shunt? Okay. So R shunt, we know that R shunt is equal to V shunt over I shunt. V shunt is equal to VM. VM is equal to IM RM. Okay. So this is the basic construction of ammeter, not multi-range, not altern. This is basic. Single range. Okay, I shunt. So IM is equal to, so this is IRM. I shunt is equal to I minus IM. So we substitute IM 100 micro, RM 1K, I is 100 milli here, minus 100 micro is IM. Okay, and this is the answer. B is just replace 100 milli with 1. Any question? Any question?
No.
Okay. This is altern shunt. A PMMC instrument has a 3 resistor altern shunt connected across it to make an ammeter as in figure 2. The resistance values are R1. Okay, so in your tutorial, okay, R1 is equal to 0.05. R2 is the same. R3 is equal to 4.5 actually. So there is a mistake. Please follow this value. Okay, R1 is equal to 4.5. Okay, R3 is equal to 0.05 ohm. Okay. The meter has RM is equal to 1K, RM here 1K, and IFSD is IM, 50 milliamp. Calculate the three ranges of the emitters. So Arshan 1, 2, and 3 are given, so you have to find I1, I2, and I3. Okay, so the answers is okay. This is my calculation. It is quite differ with the answer given. Okay, so what to find? I. Okay, so we know that. Okay, so when you please read the question. Calculate the three ranges of the emitter. We need that we want to find I. So I is equal to what? I is equal to I shunt plus IM. Okay. Okay, I equal to I shunt plus IM. I shunt 1 is equal to V shunt 1 divided with R shunt 1. Okay, so now let's start at here. Okay, I1. Okay, at I1. Okay, how to find I1? I1 is equal to I shunt plus IM. Okay, I shunt 1 plus IM. I shunt 1 is equal to V shunt 1 divided with R shunt 1. V shunt 1 is equal to VM. R shunt 1 is equal to this 0.05 plus 0.45 plus 4.5 ohm. Okay. And VM is equal to IMRM. So we substitute. IM is equal to 50 micro, RM 1K. Okay. So okay, this is for I shunt 1. This is I shunt 1. Okay, divided with R shunt 1. R shunt 1 is all the R. Okay, plus this is IM. IM 50 micro, and we get this value. Any question? Can I understand? Can?
Yes.
Yep.
Okay. So this is where the selector is tapped at I2. Okay, at I2 is equal to I shunt 2 plus IM. Okay, but now I use V is equal to V. V shunt is equal to VM. Okay, so V shunt 2 is equal to I shunt 2 multiply with R shunt 2. Okay, I shunt 2 is the current flows here. Okay, multiply with 0.05 plus 0.45 equal to, this is the voltage drop across this path. Okay, this path consists of 1K plus 4.5. Okay, this is IM. Okay, and then we get I shunt 2 is this, so I2 is equal to I shunt 2 plus IM. Okay, same goes for I3. I3, the selector is tapped here, so R3 is parallel with this. RM plus 4.5 plus 0.45. Okay, so V shunt 3 is equal to VM. Okay, so this is V shunt 3. Okay, so V shunt 3 is equal to I shunt 3 multiply with R shunt 3. Okay, R here. Okay, so R here is 0.05 only, so the rest is for the other path. This is I shunt 3. Okay, any question? This is I3. Mistake. due to copy and paste. I copy this part, paste here. Okay, so I do not change the value. Okay, any question? Okay, actually this one is 1.00505. Okay, but never mind, you can leave your answer for 3 decimal points. Okay. Or to show the difference with I shuntry, you can put like this. Okay, that's all for today. Any question? So this answer is quite different with the provided answer. Okay. Any question? Can understand today?
Yes, Dato', yes.
No
Question.
No question. Okay, so 43 of you. Ada banyak soalan rupanya kat sini. Satu ni 1K. Afiq want to ask something? Afiq?
Yeah.
Afiq nak tanya apa?
No, I just confused. Why add up 1 I2 must plus 1K?
Okay, now you understand or not?
Kinda.
Huh?
Kinda.
You want to repeat your question?
Asal dekat yang I2.
Which slide here?
Yang ni.
Okay.
Dekat yang 50 micro tu kita darabkan dengan 1K plus 4.5 kan. Why kena plus with 1K?
Because RM must be included for each calculation. Okay. Let me sketch. Okay. So this is for I2. Okay. I2 is here, meaning that okay, this is positive here. This is R3. And we have R2. Okay. Okay, and then this is negative. This is I2. I2 flow like this. Okay. And then we have RM here. And R1 here. Okay, that's why. Okay. This is V shunt 2. This is the voltage drop here. The voltage drop here is equal to I shunt 2. I shunt 2 is the current flows through here. Okay, I shunt 2 multiply with R3 plus R2. Okay, 0.05 plus 0.45 equal to the voltage drop here. The voltage drop here is equal to IM, okay, multiply with the summation of resistor here. It is RM plus 4.5 R1. Can you understand?
Yep.
Boleh?
Boleh.
Afiq ke tu? Afiq dah boleh dah?
MT.
Ha?
MT.
MT? Apa tu?
Nama saya.
Oh. Bukan Afiq eh?
I more prefer call MT.
Oh, not Afiq. Call you MT?
Yeah, I more prefer.
Okay. What is MT?
More family name.
Oh, okay. Okay, so now you understand MT?
Yep.
Okay. Any other question, class? If you cannot understand, ask now. Rather than you ask your friend during final exam and midterm test. No question? RM pun, okay, no. So no question, right? If there is no question, we will stop here. Stop recording.